Hello everyone, thank you for tuning into my video today on integration using partial fraction decomposition. So if you remember from your pre-calculus days, you spent some time trying to get this rational expression to look like this. Okay, and that is part of our goal today. That's our first goal today, because if we're trying to integrate this rational expression, as you see here, we can't do it the way it's written. But if we break it down to this, now we'll be able to integrate it actually pretty easily. So this is called partial fraction decomposition, and this is what our answer is going to look like. And if you remember from your pre-calculus stage, you probably did partial fraction decomposition with linear factors, repeated linear factors, quadratic factors, and repeated quadratic factors. We're not doing much of that. All we're going to be doing is with distinct linear factors, because that's all that will be tested on in Calculus BC. So let's look at our first problem here. Quick note, the more distinct linear factors the denominator has, the more fractions we'll have. So the first one, before we do any calculus, we need to do some pre-calculus. So first I'm going to factor the denominator here and set up two partial fractions. Each one will get a constant, a and b. So for this first one here, what we're going to do is we're going to multiply, we're going to get a common denominator here. And it's going to be a times x minus 1 plus b times x plus 2 all over our common denominator. Still equals this. But now if we multiply through by the denominator, it's gone. So we're left with is 1 equals ax minus a plus bx plus 2b. So now I can set up a system of equations, my x's and my constants. There's no x's, that equals a plus b, and there's one constant, that equals negative a plus 2b. And then we're going to solve that system. This one is set up for elimination, so let's add through. We get 1 equals 3b, so 1/3 equals b. Put that back into here. 0 equals a plus 1/3. So then subtract the 1/3. We get a equals negative 1/3. So now I can rewrite my integral as negative 1/3 over x plus 2 plus 1/3 over x minus 1 dx. And now we can simply integrate. Now you can, I guess I'll write it out like this so you can see how this is going to work. This is what we're going to be thinking, but we don't need to actually do all this work because we should be able to do this integral without writing this out. But this is what we're actually going to be integrating here. And it's going to be negative 1/3 ln absolute value of x plus 2 plus 1/3 ln absolute value of x minus 1 plus c, of course. Okay, here's another one. So this has three distinct linear factors. How do I know that? Well, let's factor this. So denominator is going to factor to x times x squared minus 1, right? That's going to be x times x plus 1, x minus 1. So I have 3x squared minus 7x minus 2 all over that. So I should have three distinct linear factors here. A over x, b over x plus 1, c over x minus 1. All right, so now if I get a common denominator here, it's going to be a times x squared minus 1 plus bx times x minus 1 plus cx times x plus 1 all over that denominator. But like I said, we're going to multiply through by that denominator, and it's going to disappear anyway. So let's just skip that step for now. We get ax squared minus a plus bx squared minus bx plus cx squared plus cx. So my system is going to be a three-tier system, the x squared, so 3 equals a plus b plus c. negative 7 equals my x's, so negative b plus c. And negative 2 equals my constants, which is just negative a. So that first one, obviously, a is 2. Then we can put that in here. Actually, we can't put that in there. We can put that in here, and we get 3 equals 2 plus b plus c. So 1 equals b plus c. And now I could take this and this and make a new system that I could solve for via adding through. So I get negative 6 equals 2c, negative 3 equals c. And if I put that back into here, I would get 1 equals b minus 3, so 4 equals b. All right, so now I can set up my integral here as 2 over x plus 4 over x plus 1 minus 3 over x minus 1. So my integral is going to be 2 ln x plus 4 ln x plus 1 minus 3 ln x minus 1 plus c. All right, so we got one more, partial fractions, but we have to do long division first. How do I know I have to do long division first? Because we talked about this when we did long division. If the numerator is a higher degree than the denominator, you want to do long division before you do anything else. So let's do long division. Now, we don't even know if we'll need partial fractions yet for this, but obviously, if they're in our video today, we're probably going to need partial fractions on it. But just looking at it, we're not going to know yet. 2x cubed over x squared is 2x. Subtracting, we get 0, 0, and plus 1x plus 5. So now I can rewrite this as the integral of 2x plus x plus 5 over x squared minus 2x minus 8 dx. And this is what we'll use partial fractions on. So, setting up my partial fractions here, I get x plus 5 over x minus 4x plus 2 equals a over x minus 4 plus b over x plus 2. So that's going to give me ax plus 2a plus bx minus 4b. I hope you're okay with me skipping a step here. And now my system will be 1x equals a plus b, and then 5 equals 2a minus 4b. So to solve this, I would probably multiply the first one by negative 2. So I get 3 equals negative 6b. So b is negative 1/2. Put that back in one of the original equations here. So I get 1 equals a minus 1/2. So a is 3/2. So now I can go back over here and rewrite my integral as 2x plus 3/2 over x minus 4 minus 1/2 over x plus 2. And now it's a pretty easy integration. 2x squared over 2, or just x squared, plus 3/2 ln x minus 4 minus 1/2 ln x plus 2 plus c. Okay, that'll do it for our video today on integration using partial fractions. I hope you enjoyed it. We'll see you again next time.